Yeah, thanks a lot for the kind introduction. Yeah, my name is Sebastian Bittrich. I'm with the RCSB PDB, and I want to talk to you about some recent developments at rcsb.org, namely a structure motive search engine that allows you to search in the whole RCSB PDB archive within seconds. And I also want to show you how this algorithm readily scales up to millions of structures by applying it to the AlphaFold database. And I guess in relation to the attack we just saw, I have a slightly different definition of structure motifs. So when I talk about structure motifs, I mean like a handful of residues in a characteristic geometric arrangement. So maybe you're looking at the binding site that has like 5 residues that are actually forming non-covalent bonds with a ligand. Then that's what I consider a structure motif in this context. Or maybe you're you know about some catalytic site that is described in literature or maybe in a curated resource such as the Catalytic Site Atlas. So our motivation was to develop a tool that can search for basically arbitrary user-defined structure motifs and can deliver results within seconds, because that's like kind of our philosophy that nobody wants to wait a long time for results. So it would be really nice if you can deliver results, you know, quickly and basically incentivize users to refine their query and to basically run iterative searches that can be refined on the fly, and that really encourage you to like explore the PDB archive at the end of the day. And throughout this talk, I want to give or want to use one example in form of the enolase superfamily, which can be accurately represented by a 5 residue structure motif. So if you look at this, conglomerate of amino acids, you can see that there are 5 residues that are actually close to a metal ion in this particular example. And the interesting thing is that certain positions allow for some genetic variability. So for example, for the first residue at the top, this lysine at position 162, it's not a lysine in all cases, but throughout this superfamily, it can actually be replaced by a histidine, and due to similar physicochemical properties, both are fit to fulfill this biological function. And the same is true for 2 other residues. So you also have like this this set of a glutamate or an aspartate or an asparagine that can fulfill a certain function at position 245. And at the end of the day, I think like structure motifs are a really nice way of addressing the enormous complexity that is inherent to protein structures. And if you run like any comparative analysis, you always run into this issue that you maybe align a really small protein to an enormous complex. And I would argue that structure motifs are like one way of normalizing this complexity and basically breaking down protein function to the essence of a protein, and to really focus on what you're truly interested in at the end of the day, which is protein function in most cases. So again, it would be really nice to offer such a tool, you know, to all of you. And that's actually possible. So everything is like fully integrated into a search system at rcsb.org. So feel free to use it. And I want to walk you through how you would actually dispatch a search, because I think you can imagine that it still is pretty difficult to define a structure motif, and it would be a pretty convoluted input form that you would use to define which structure you're actually looking at and which residues you want to extract to define your structure motif that you want to then at the end search for in the whole PDB archive. And if you use our service at all, or PDBE for that matter, I think you're familiar with the Monster 3D viewer. And basically you can start interrogating your structure like any other structure, just moving over to the 3D view and having a look at your protein structure. And again, like within this highlighted region, there's this metal ion. So maybe you use some ligand to basically navigate to the interesting part of your structure. And then you would manually select those surroundings by selecting those residues within the Monster user interface. And on the other hand, you got this view at the top of the panel, which shows the sequence. So maybe you're also coming from some literature that describes the residues of interest by their sequence positions. So you can also approach the problem from this angle and use the sequence panel to define your structure motif that, again, you extracted from literature. And at the end of the day, you will fill up this panel on the right-hand side, which shows this structure motif search component, which gives you a summary over the, in this case, 5 residues that you actually selected and that you want to search for. And as stated before, it's quite common that you want also to support those position-specific exchanges where you can have multiple amino acids actually implementing a particular protein function. And you can do that at this panel at the very bottom where you can see histidine at position 295. And you can say, okay, it's not just the histidine, but the lysine also gets the job done. And please consider both in your search run. And once you have all of that in place, you can hit submit search. And when you do that, basically a new browser window will be opened on a new browser tab, which takes you to the default result page of rcsb.org. So you basically see at the very top a summary of your search query. You get this list of all the structures, in this case assemblies, that matched your query. You can navigate this result set. And I think like one of the nicest aspects is that you also get this refinement panel on the left where you can, for example, specify that you're only interested in protein structures with a resolution that is better than 2 angstrom, or maybe you're only interested in one particular organism. So I think it's a pretty powerful search system. And I really want to point out that the structure motif search algorithm is fully integrated with all other search services. So you can readily combine it with a sequence search, with a global structure alignment, with any keyword-based search or search for chemical components or ligands that should be present in your structure. So I think it's like pretty powerful that you can pretty easily define really complex queries at the end of the day. And if you focus in on one particular result item, you can see like all the usual meta information. And at the very bottom, you get this structure motif match context, which basically gives you a summary of the individual amino acids that were matched to your query motifs. So for example, this lysine at position 188 corresponds to your first residue that you defined in your motif definition that you're actually searching for. And you can also see the RMSD value that was achieved by an all-atom alignment between your initial motif definition and the hit that was found in this particular structure. And last but not least, you can click on this alignment button, which will take you back to Monster and basically come full circle and align your query motif to the occurrence of this particular motif in this particular structure. And then you can investigate this alignment and try to make sense of it, interrogate the structure, whether there's a ligand present in both cases, or maybe the ligand is absent in one of those cases. So things like that. And last but not least, it also, again, allows you to run this iterative process where you can then redefine your query. So you can launch another structure motif search if you really want to, and maybe eliminate one of those residues that is like, that you deem pretty flexible, or maybe you want to include another residue to make it more specific and by adding more constraints to your search query at the end of the day. So that's like the overall idea of this algorithm. And for the second part, I want to show you how this approach scales. And I also want to give you a high-level overview over how this is actually done and why the system is fast and can deliver results in a matter of seconds. So we heard that like many, many times before, I guess, but we are in the fortunate position to have like a lot of structured data at hand, but that also requires that we have good tools at hand to make sense of the structured data. And the PDB archive gets more and more difficult to navigate because it's difficult to find those cross connections between protein structures, and some structures may be really well studied and some are, we know the structure, but maybe we don't really know what's going on in that particular entry. So, and we're still living in a time of tremendous growth. So we had like 100K of structures in 2014, and next year we'll surpass 200K of structures. And at the end of the day, all of that is like pretty lovable if you consider the fact that we have 1 million AlphaFold models at hand. So 400K were released last year, 600K in addition to that were released this year, for a total of 1 million, give or take, computed structure models. And yeah, I think, again, there's so much more to come if we trust the announcements of PDBE and DeepMind. So yeah, we basically need search tools that can scale up to millions or hundreds of millions of structures, and we need them fast, again, to make sense of this pretty unexplored space of new structure data that has surprisingly high quality. So again, it would be really nice to make like any relation or find any like correspondence between PDB structures that are well annotated and, for example, anything that's within the AlphaFold corpus. So in terms of scaling, again, PDB roughly contains 200K worth of structures. And if we form the largest data set that you might want to search in, you arrive at 1.2 million data items if you basically combine the PDB archive and everything that is currently in the AlphaFold database. So it's a factor of 6, which is, it should cover us for many, many years of structures getting added to the PDB archive. So this algorithm, hopefully, if it can tackle this amount of data, then hopefully it can, survive a decade or so before we need better methods to search for structural motifs. And in terms of runtime, going back to this example of the Enolase superfamily, searching in the whole PDB archive without any pre-processing, without any like redundancy filtering, that would be mandatory as a pre-processing step. You can search in roughly 200K of structures within 1 second. So I think that's pretty remarkable. And in terms of scaling, if you move up to 1.2 million data items, it takes roughly 3 seconds, which isn't horrible and which still like incentivizes users to, not go for coffee, but to stick around and to wait for their results and to have a somewhat pleasant experience when searching for data. And to give you another quite prominent example, I also included the zinc finger motif, and you can see that motif gets processed in 135 milliseconds, and it scales up to 840 milliseconds if we search in 1.2 million data items by also including AlphaFold DBs. So again, I think that's a pretty reasonable scaling factor in terms of runtime, and this trend holds true for basically any motif you can come up with. So I only included those two for visual clarity, but yeah. And I think one remarkable aspect about this is that you don't only get a list of all the structures that contain your structure motif, but there's actually some work being done on the fly. So you get all atom alignments, or you can actually define if you only want to align your backbone atoms, if you only want to align sidechain atoms, or all atom alignments. So whatever is most reasonable for your use case, those alignments get computed while all of this is happening. And RMSD values are reported, transformation matrices are reported. So you got a lot of data. And I think that's especially remarkable if you, again, consider this example of the zinc finger motif, which actually performs 36K worth of alignments in under a second. So I think it's like the other take-home message, that we really need algorithms and strategies to deal with structured data. And yeah, I think this conference was pretty exciting. So soon after the release of AlphaFold, and there were posters about structure compression tools, and also the next talk in the session, FoldSeek. So I'm really looking forward to, again, any way of tackling this amount of structured data. So I'm really delighted to program software nowadays. So, and last but not least, I promised you to give you a high-level idea of what's going on in this algorithm. And there's not really a whole lot new under the sun. So everything is based on rotation invariant geometric descriptors. And what I mean by that is that if you have any structure motif, like a catalytic triad, for example, composed of 3 residues, you can define or look at all the 3 residue pairs that you can define for this particular query you might want to search for. So that means that there's this pairing of the aspartate to the serine, And you want to find similar occurrences of an aspartate next to a serine, but they're not just next, but they're in a certain geometric arrangement. So they have a certain relative arrangement to one another. And that's captured by those 3 integer values. Don't care about any of the details. But basically what this allows us to do is to have this, again, rotation invariant description. And it basically allows to have like a pre-processing step that computes in half a day for the whole PDB archive. It captures all of those residue pairs and it writes them to a database or any data structure that you want to use at the end of the day. And this allows to basically group together all occurrences of an aspartate and a serine that have this particular geometric arrangement. And you can imagine that this is really valuable information if you want to search for, any occurrences that is similar to what you're looking for in your query motif. And you do the same for all the other residue pairs that you can define. And this basically translates your query that has like really high complexity with like 3-dimensional coordinates into an expression that is like really easy to query, really easy to process computationally, and that is also fast in delivering results. And how all of that is useful at the end of the day is that it basically allows you to really elegantly and efficiently navigate your search space. And what I mean by that is if you, again, look at the first constraint, then you will see that this particular geometric descriptor, it doesn't contain, it's not contained in all PDB structures. It's usually the trend that those residue pairs are only occurring in like 1/3 of your search space. So that's already a pretty substantial speed up at pretty much no cost. You have this pre-processing step, but then your search is like really fast. And things get interesting if you have more constraints. And what will happen is that they land in a different region in the search space. So there's some minimal overlap, but there's only a small like intersection between those sets that contains both those residue pairs. And you do it again for, as long as you have more residue pairs in your query to process. And you will see that you basically at the end can pinpoint this really tiny region in your search space that contains structures of interest that are highly likely to contain structures that are similar to your query motif. And also this is a word level inverted index, which means you're not only getting the PDB ID that you should look at, but you also readily identify the sequence position that corresponds to your first aspartate. So again, this also makes it quite easy and fast to compute alignments. And yeah, to sum things up, I presented to you a strategy that allows you to search for arbitrary definitions of active sites or other structure motifs. I showed to you how this algorithm scales to millions of structures. Everything is fully integrated into RCSB.org. You can check it out on GitHub. It's open source in a Java implementation, so you can also run it on your local system if you like to. Totally encourage that. And last but not least, I would like to thank the whole RCSB PDB team, especially Stephen Burley and Jose Duarte, who are supervising this project. Nowadays, I would like to thank Dennis Peel, who is in the audience today. And I would like to also thank Alexander Rose, who initially supervised this project, and Florian Kaiser and Michael Schröder, who really molded my understanding of protein structure motifs. And last but not least, we are always looking for talented software developers. So if you are interested, or if you know anyone who might be interested in joining the RCSB PDB and developing software that basically reaches millions of users, then feel free to reach out or spread the word. And yeah, thanks a lot. And I'm open for questions.